invitation so I can talk a bit about this natural language processing journey. The objective of this talk today is to give you a glimpse on what is working with text, what is it all about, what have you been doing in the past, and also a bit of how did actually deep learning impacted the area. Does it mean that nowadays we should, forget what we had done in the past and do everything with NLP, with deep learning? So it's just a bit of that. And then feel free if you actually, I like to make this interactive. So if I am actually saying something in a slide that, jumps a question, feel free to ask me. I'll be glad to do it on, let's say, real time in a virtual way. All right. So having that said, why do we hear more about NLP today? I would say that what actually happened in the past year is that natural language processing quite grew a lot in the industry. There's a lot of reasons for that. So we have the processing power, and we also have something that we did not have in the past, which is a lot of information available online, which allow us to engage with different industry applications through NLP algorithms. So I'm here showing you a couple of examples. So I would say most of you already heard about Alexa from Amazon. You also have other tools. I have here an example. This one is it's Tianxi. I'm not sure if I'm spelling it right, but it's actually a virtual buddy. And it's quite popular in China, so you can actually be friends with an AI. So this AI is talking with you, is engaging with you. And if you think about the complexity of what you have behind, it's super exciting. And this is something that we can do today, right? And so we have like this idea of the virtual companion. We could think about also customer service. So more and more we see chatbots being made available. The idea behind is probably a lot of the questions that we have, a chatbot can answer them. And we don't have to go and take all the long time making calls and so on. We just clarify our doubt there straight on. So that's also one of the biggest advantages. And there's a lot of work as well on making them more humanized in some way, and the way they engage with us. All right. So these are some of the industry applications that have been growing a lot in terms of the quality of what they provide. And in academia, you have a lot of work has been going on. So what I see is that today we are actually taking advantage of a lot of work that was done in the past, and we are able to scale it up, basically. That's what's going on nowadays. And one example of the tipping point I see, it was when IBM Watson won Jeopardy. So this is a quite popular show in US. And basically what happens in this show is that you have something like trivial game. You have a question that is made, and it can be about mainly anything. So it's just like cultural knowledge. And you have a lot of people who compete in here. And if you know it, basically you answer all those questions and you won. So imagine the idea of you having a machine that is able to make the interpretation of that question and provide the correct answer. Because you can actually feed a machine with a lot of knowledge, but it's not easy for you to, to implement this question answering to actually get the right answer in place, like the first answer that your algorithm gives. And I see this as a tipping point because it was so popular that made a lot of interest from the industry to use NLP algorithms. And another example, but now from the academia. So if you go and see a lot of things that were being done and how they were actually shown, well, I would say one of the challenges, if you are working in industry, is how can you show value from everything that you are doing with text? And usually what you have is this type of this is a possibility, right? One of your analyses that you might do is a graph like this. And what you are seeing here is when you have concepts being associated with different categories. So here you have like computer companies, brokerage houses, and then the algorithm was able to identify different terms that are associated with them. So you could see it as if like a semantic relation between those terms, all right? And they can even share each other. And you can show this in a graph, right? So this is just for you to have an idea. It's from 1997, so it already has some time. What is the difference from today? Well, a lot of things that you are seeing now with deep learning, those word vector models that people are doing, they are actually doing this. And these connectors many times are those semantic similarities that people talk about, right? And this allows you actually to answer a lot of things. So if I actually want to know who is mostly related, for example, with computer companies, and I want them to be people, so I want them to be within the person's entities, I'll be able to get a collection of documents, put it in there and say, hey, we have Alfred Goldman, we have Bill Milton, and Billy Kong belong to the computer companies. Okay, and this is done automatically with a collection of documents. So it's just one example of one of many things you can do here. Another example that I think all of us saw, and now it's like common practice, was with Obama elections. And this was back in 2009. And this was a time, so in US, they have actually, in terms of if you are data scientist and you are working with data, you love the fact that in US, you can use Twitter, because it's publicly available and you can actually take insights from it. And what they did then was, while they were doing their, they are running for president and they go through the different states, they could actually look on what people were reacting for different things that were being proposed. So we can think about, the economic education package, the economic package, and so on. And you could actually analyze what people are saying within each state, and then align, the speeches that they were doing, and even maybe change some part of their proposal during the campaign. So adjusting towards what people were saying. So we are actually being able to take insights, not from small surveys. We are able to do this in a large scale. So that was really, really interesting, because we could see how we could use this information to learn from it. And in the end of the day, Twitter, think about it, it's texts, it's not structured. And we are indeed now able to take insights from it, and they are actually have a strong impact. And here it was in elections for the presidency. And finally, this is a project that I did. And it's just another example. This was an academic work, but it had to, so here I like to show this example of when you are doing something in academia and you get the opportunity to show it in the industry, how can you make, this bridge? So I had done at the time a reputation algorithm, right? So what I said is, imagine if I am able to know the reputation of different entities. Here I had names of actors, characters in movies, even, names of movies, and I had a reputation. It could be quite good or bad. But then a follow-up question could be like, okay, and from my domain, who contributes the most to my reputation? So I might like to know, if I'm Christian Bale, that Clint Eastwood, actually it's a super positive relation that I have towards my reputation. While then you have other ones that actually it's a really negative impact that they have on me. And then this is an example, but think if you are in the industry and you are, for instance, Amazon, you want to know who's pushing me up, who's pushing me down, and then act on it, right? And again, this is automatically done through a collection of documents. And here are reviews from IMDb. So what people gave their feedback on different movies. All right. So this was just a context, just to give you a glimpse on the different exciting things that you can do with NLP. But now I just want to go more on explaining you, how can you do this work? Which are the steps that you need to be aware of, right? And one of the things that I like to clarify is the difference between data mining and text mining. Okay, and text mining, you also have text analytics, which is basically the same, but it's not the same as data mining. And you can put it in a very simple way, is that when you think about data mining is structured data. So it is already kind of like in a structured form. You have a tabular format, right? As if when you go for text mining, it's not. So it's completely unstructured. And a lot of the work that you do, and it's some of it that I'm going to talk to you today, is actually going into that unstructured format and define your structure. And that will be the structure that you use later on for your models. And that can be quite challenging according to the data that you have to start working with. All right. So that's, I like to make this clarification. So if you see data mining somewhere, it does have some common things, but it's not the same pipeline. The other thing that you could ask is, well, I'm in academia and actually I would like to pursue this area. Where can I actually find text mining? And this can actually be quite confusing if you're still a young graduate. And why is that? Well, because text mining is everywhere. That's actually the reason. So that's why I'm providing this this slide, and it's actually from a really nice set of slides that talks about the area. But the message is here is that you might like text mining, but how do you want to explore it? Do we want to explore it purely on a natural language processing background? So you are very focused on text and the semantics and so forth. So it's very specific. It's like you have, usually this work is many times done with experts from literature because they are very good in that area. But you could say that, no, I want to explore more, but I'm more in the perspective of question answering, more in the perspective of, you know, search engines and so forth. So then in that case, you might be more interested in seeing work that is done more in the area of information retrieval. Or giving you a last example, if you are more into, I want to improve all these algorithms, like I want to make them work really, really well. So you're more focused on the algorithm itself and not its application, then you should go more for areas from machine learning, like ECML, NIPS, and so forth. All right. So in there, if you go, then you get the papers from there and you get a glimpse on, yes, they talk about working with text, but then they actually tune in different directions. All right. All right. So now going into what is all about working with text. So as I told you, it's not really well organized. You can actually take like a lot of ambiguities in the text, and not at all times you actually have the nice thing of having annotated data. Annotated data allows you to learn some algorithms which are dependent on that, but other times you just have to go to purely unsupervised models. And you have both roles, and you could say that you have the positive and negative side of it. All right. All right. Challenges. These are two common challenges that it did not change over time. So you might have a lot of computing power, but that doesn't mean you don't need to worry about these two particularities. So dimensionality, why is that a problem still, right? You could argue, but well, I have a big machine, I can go into the cloud, right? But the thing is, when you were working with text, think about the text itself as a unit, right? And I can say that, for instance, words, single words are units. Okay, so you could look at collection of documents and you have like, let's say, 1 million of different words. Okay, but then you say, okay, but this is not good enough. Because if I want to do an analysis, for instance, for the elections, for me, a bigram such as president of the Republica makes a difference. So I want that bigram. Bigram, why? I have 2 words. So then it scales up, right? Because I had that 1 million and now it's going to add on top of this. And the thing is, the problem with text is that these units, which is the text, the way you represent text, it can grow exponentially. It's too much. And you have this matrix that becomes huge in terms of columns. And also it doesn't provide much value. And this is when we come from the feature sparsity. Why? Because some of them are so specific that maybe you saw it happening once, but it never happened again. So it means that from the different documents that you will have a lot of zeros. So in the end of the day, this, for the different algorithms that you might use, it poses like a big challenge. The other challenge that you have, well, I'm talking it's a challenge, but doesn't mean you don't have a solution for it. You have, but you need to bear that in mind when you're working with, okay? Another thing that you need to be aware of is the documents that you have as a starting point. And usually you might hear these terms like weakly structured or semi-structured documents. So what is the difference between these two? So the difference is you might have like a completely free format, right? So it's the first box that I have there. It doesn't have much structure to it. And so it means that in the end of the day, you cannot rely on a set of rules that you know that, for instance, text should be within that box. So when I put, for instance, my parser, I'll go there straight away. Sometimes you don't have that advantage. So what does it mean in the end of the day? It means that you get more noise. And then that noise means you have an additional set of work to clean it before you go into your models. Because if you have too much noise of things that you're not really that relevant, in the end of the day, your final model will have low quality because you didn't take the time preparing it in a proper way. All right? Then you have another type of documents, which you can call it semi-structured. I'm giving you here some examples, HTML, PDFs, and so forth. Imagine that I'm doing a crawler, for instance, on LinkedIn, for example, right? So it's HTML. Let's put it an example. They don't provide me an API, so I actually have to scrap it. So I have HTML, but HTML actually it's quite nice because it has some format to it, right? So I can know what is the title, and this means when I'm doing my parsing, I know the title is always there. So I have this semi-structure format that allows me, when I crawl the data, to know what it refers about. Is it the title, for instance, news articles? Is it the title of the news articles? Is it the body of news articles? Is it the name of the author? All right. So that's the advantage of working with semi-structure to it, because you actually have some sort of labeling to it, because the format itself allows you to know that. Okay. So imagine at this point, you're not concerned anymore on getting the data. So you already went through the semi-structured format or the free format, and you have the data on your end. And what do I need now? What should I be concerned about? So I'm going to talk to you a bit of some of the steps that you can go through and what do they mean, and also why do we do them, all right? So we can think about the first step, tokenization. Tokenization means it's one way of saying you have a token. Token is how you're representing the text. So tokenization, one common way is to do it is representing by words. So your token unit is words. Then you have the tagging. So tagging allows you to know, is it a verb? Is it an adjective? And so forth. And why do I want to know that? It depends on what you are working with. So if I'm working in a sentiment analysis model, for example, I'm actually quite keen on understanding where I have the adjectives, because adjectives are used to, to push up or down when I like something or not. They're commonly used to do that. So for me, it makes a difference to know which label, so which tag does my word have, all right? And then you have the chunks, which basically is how you chunk you take out parts of the text, and stemming and lemmatisation. All right, so I'll explain those later because I think it's easier with the examples. Okay, so tokenization. I have a sentence, we are studying tonight. If I say the token is separated by space, I have the tokens, we are studying tonight, and then the final dot. All right, so this will be what I'm going to work with after that, if I do tokenization like that. Then you have here an example of what is the output if I run a part of speech tagging. So part of speech tagging is basically going to pick up that sentence and it's going to tell me that we is a pronoun, we have are and studying as verbs, and tonight is a noun. All right, so this is what automatically it gives you back. So as you can imagine, a lot of things that we are using in NLP are language dependent, and part of speech tagging is language dependent. All right. And notice that in all the slides, when I am showing you these things, you have here the link. So if you want to explore more on what I'm showing here, you are able to do it, okay? And dependency parsing, what is this? So imagine that you have the sentence and you want to understand how they influence each other, all right? So in here, basically, I'm able to see that studying is a noun subjective to we. So when I'm looking at studying, who is studying? In this case is we. And we, if you had more context before, you could know perhaps even the names of the people, all right? So this is also relevant, again, giving you a sentiment analysis example or even repetition. Basically, if you want to understand if a given entity, which is, for example, a person, who in the text, what is actually impacting directly the person, all right? So that's one example of why you want to do that. All right. Another example is the modifier. So this also allows to know if you have a modifier. So if you have negative terms and even other terms that intensifies adjectives to make them like with a higher connotation, then it's also really nice for you to have the dependency parsing. So if you put this all in place, you can think about it this way. I have I have a sentence, a dog is chasing a boy on the playground, right? Then I do the part of speech, the part of speech here. So I get the nouns, how to get the verbs, determinants, and so forth. And then I can do the syntactic parsing, which allows me to see how they are related to each other. All right. So in the final end, I may be able to, you know, infer what's going on there if I have all the steps done. All right. And if you think now on the chatbots and so forth, this is the type of things that they are doing. All right. I'm actually excluding the chatbots that are using rule-based. That doesn't matter because they are not learning anything. They're just waiting to get a set of questions and they learn. I'm talking about those chatbots that are actually making an interpretation of what you're saying. Okay. All right. So going back to the tokenization, I told you that it's commonly used the word level, but that doesn't mean it's what you should always do. And actually, an important learning here is that when you are doing NLP, each problem is a problem. So, and actually, this applies to a lot of fields of from data science. And here is another case. So I might be doing something that actually my unit is a paragraph or even a sentence, okay? So a common example is if I'm doing summarization, usually on summarization, I don't want to go to such a low level of representation such as the words. And usually on summarization, I do like to use a token, which is a sentence or even a paragraph, all right? And summarization algorithms, what they aim to do is, imagine that you have a repository of news articles and you want to give automatically a glimpse on what that article is about. So people click on it, but they have something more informative than just a title. So you want to automatically generate this summary. So in that case, usually the algorithms uses either paragraphs or sentences to then build this automatic summary, all right? And there are the reasons, and also sentiment analysis is again a good example of why you also many times want to use sentences. All right. Strategies. So I took this and I put this as a vector. So just, you know, just to give you an idea, because when you are running this on a language, a computer language, you will have this represented usually in this form. Okay. So in each position, I have all those tokens. So what should I be worried about? It's when you start, you know, doing your cleaning, right? So it's commonly done to take characters that do not provide much information. So for instance, the dot, the paragraph, it's usually removed. I might use it to extract my sentences and then I just drop it out. What is my warning here? Be careful on what you are working with. For example, if you are working on something that is regionally relevant, be sure that your region does not have this type of patterns, right? So Many times USA it's written in this way. So if you see this point and you separate, you lose the country information, okay? So sometimes when you are doing your preprocessing, what you do is you create exceptions. And those exceptions are done for your work that you are focused on, all right? And you, of course, you're not gonna do this manually for everything. You only do for those that you know that are relevant for your business, basically, for your business case. Another thing that you need to be worried about, and these examples are for English, but then for other languages, you would have other examples, are the contractions. So in English, you have things such as don't, that's, which in reality, don't is a negation, so it's do not, and that is. So what happens is, if you take that special character, what does it mean? It means that you lost precious information, all right? And this that you're seeing here, verbs and the negation. So the first part, I got it with the parts of speech tagging. And the second part, I got it with what I was showing you with the syntactic dependencies. All right, so it's I think it's more clear, I hope, on the advantage of doing both, because in the end I know that I have a negation and also this dependency that goes on, this negation that goes on the verb do. Okay, so if I put everything in place, so when you run this on a sentence, it basically gives you back an object with all your words and their associated part of speech tagging, and the same thing goes for the syntactic parsing. So you would have something like this, right? I have dinner before starting text mining class, and then you have the pronoun, the verbs, and then you have different types of verbs. It even tells you that this is a verb, but it's on the third person singular present, and so forth, all right? So a message here. I'm showing you an example here. It's from PN3 Bank. You might use different libraries, which means that they might have different labels. So you're not supposed to know this by heart. Usually what we do is when you choose to use a part of speech tagger, basically you consult to know which are the labels. Because in the end of the day, you are going to use the labels for your analysis. Another thing that are commonly done and people really liked it after they know about it are the stop words. So what are the stop words? Well, they are known as those words that come with little or no semantic meaning whatsoever. And what people usually do is, well, I'm just going to take them all out. Why? Because they are super noisy. They don't provide any insightful information. So imagine that I have a collection of documents, and those documents represent books. And I have a task, which is I want to have a classifier to tell me this book is from history and this book is from science, right? So I'm concerned on knowing all the terms that are highly related to history and science. So words such as the examples I'm showing you here, and, as, be, could, why, who, well, basically they don't give me any information whatsoever about science or history. Why? Because they are usually used as connectors in a given language, in this case English, right? So I just drop them out and I keep going as I go. And this is also an important part for the dimensionality problem that I told you about. The thing is, it always depends on your problem. So just a quick example. Imagine that your challenge is you have a collection of documents and you don't know the language of those documents. So you have English, you have French, you have Russian, you have all these different languages, all right? And what you want to do is, I want to learn if this document is from English, if this is from Austria, and so forth. And in here, it's really interesting because it matters, this tokens, so they are super relevant. And another thing that is super interesting is that a super relevant token, it's not words, it's the number of characters. So if you use the first 3-4 characters, they tell you a lot about the language that you are working with, right? So be aware of this. You will only remove according to what you're working with, right? So if you are wanting to make a distinction between English and, for instance, Portuguese, the word and will happen a lot in English and not in Portuguese. So it's a relevant word, right? And the final message that I want to tell you about stop words is that usually when you're using it, an NLP library from different languages, you have Python, R, Java. So when you're using, usually they have already a set of stop words available for you, so you don't need to manually go for them. My advice is have a look on them. See if you have any stop word that you actually don't want to use it, so you remove it, you don't apply to your data. And the final message is, if you are doing different sets of work, so imagine if you are from the area of, you are working in the health or biology, in those areas, they have a different set of stop words. So stop words can actually be very specific to different domains, and you don't need to do all of them from scratch. See what the community already has available for you. So having that said, these two links that I'm sharing with you here, you are able to have a deep dive on different stop words that are made available from different researchers, right? Okay. So the name entity recognition, and I actually mentioned chunks. So why? Because basically when you run a name entity recognition algorithm, it's also known the output as chunks. So it's different terminology to the same thing, okay? And the objective of these algorithms basically is, I have again a collection of documents, and imagine that you want to know automatically tokens that are there, but actually are referred to specific entities. And what are those entities? Well, the entities can be a person, it can be an organization, it can be a location, and so forth. And this is quite practical if you have a large collection of documents, because you might have want to understand who are they talking about. So in that case, you go for the persons. Right? You might be concerned on saying, okay, well, people are talking a lot about these different things, but is it focused on a specific region? Well, you don't have to do anything that it's manual, because you are able to use these algorithms to extract it from you. All right? This is, again, an example of an output from one algorithm. This one is available in NLT key, so Natural Language Processing Toolkit from Python. But if you go to different libraries, so for instance, now you have a lot more libraries available in Python, you will see that the entities names are not exactly the same. So why is that? So it depends on the implementation itself. It's the same rationale as the sparse-of-speech tagging, okay? So what do? As soon as I decide to use that library, I will see which are the entities that they crawl, and based on that, I will know which labels I want to use, right? So if I run my collection, I want to say that I want to know all the labels that are the algorithm gives me as person. And then I get President Obama, France, Beckover, and so forth. Okay, so that's the advantage. But I need to know which entities I'm actually getting, and it's dependent on the implementation that was done. Okay, but the principle is exactly the same, right? In terms of what it's doing. It's returning to me these chunks, which have some context to it. What else? So this next two slides is just to give you some glimpse on challenges when I'm processing text. Well, actually, why am I processing? Well, I'm building my structure, and my structure will be how I'm going to represent my documents, my textual documents, to an algorithm. And I have a lot of things that I can do. That's why I'm giving you here this example. So when do I give all the trouble to, go through all of them? Because it has two things to it: your work and also the processing power to it. You do it when it's relevant to your challenge, okay? So I might be concerned on knowing, for instance, if a verb was in different terms, if it was in the past, present, or future. So I'll do the part of speech tagging, and when I look at the verb, that's really relevant for me. And then I might be concerned about the modality, if it's conditional, imperative, and so on. So all of these things, you can actually have some knowledge from it when you pass it to this type of algorithm, such as the part of speech tagging, all right? So it gives you actually a lot more information than the one that I showed you in those examples. Another thing is the contractions that I told you about. So this is just a more specific example. So the don't I showed you, right? So you can actually know if you cross it. So you take that in consideration. So you know that it's a negation over the verb do. And then you have other things such as the example that I gave you in the second sentence. Peleja's dog is a Belgian Shepherd. It's not a contraction, it's a possessive, right? So that's why you need the full sentence to be able to do it right. What does it mean as well? I only do the stop words afterwards, right? So the name entity recognition, part of speech tagging, they need the text as in a more raw format. And then after you do all this analysis, it's when you start, okay, now I'm going to take out what I don't care, okay? So you don't lose, for example, the entities such as person, locations. For example, the uppercase there is super relevant to know that it's a person or a location. Okay? So these are just some examples of other things that you can get. Plural, gender, possessive, and so forth. You might commonly see this, rejects patterns. So my advice is, as soon as you are comfortable with all the cleaning that you want to do, use rejects patterns. It gives you some, if you have to build everything from scratch, it might give you some work to it, but it's totally worth it in terms of computational power, all right? So if you are doing loops to do cleanings and finds, etc., it will take a lot longer. And if you have a large collection of documents coming in, this will make a huge difference, okay? And if you want to try it out, try it with and without, and then you'll see the difference. Another thing that is super helpful is the contraction maps. So some of the examples I gave you are, let's say, commonly existing in your language. So you might find it available in the libraries, available expanding contractions. So this contraction map basically will do something like this. I have isn't, I have isn't, and it will map it to is not, aren't, are not, can't, cannot, and so forth. Okay, that's the advantage. And actually, for the most common ones, it will resolve you a lot of the cleaning process that you need to do. Okay. All right. Another advice here is that think about this way. You are preparing this for a machine, right? And if you are preparing this for a machine, the machine makes everything, all the subtle things that are there. And maybe we as human, we see, okay, this is the same thing. But for the machine, if it's not written exactly in the same way, it will be different. So if I have, for instance, the word here, word written with uppercase and so forth, it's for the machine completely different from the word all in lowercase, okay? So what do? One of the normal things to do is I'll go for my text and I put everything in lowercase. And that's how I represent my text. Again, a warning. So if part of speech tagging and name entity recognition, they are basically trying to identify certain patterns. So again, it's relevant for you to do that before, and then you have all your entities identified, you have all your basically all your chunks, and then, you know, part of speech tagging, you know, all the verbs, the nouns, and so forth. Okay, now I have that information, but now I'm going to put it all cleaned, so the final output. What does it mean? You are providing different sets of information. So I have a document, it's all in lowercase, and I know that in that document, I have the entity President Obama being mentioned, all right? Because I did the name entity recognition before doing all the cleaning, all right? All right, okay. So another example is you might notice that when you are typing, for instance, in the emails, Google Mail, you see that a lot. You are typing and then it suggests for you a correction, even on the search engines. So many times what happens is that you have common mistakes even based on your keyword, right? So There are different ways of doing this, but you could actually have, again, a large collection of documents where you can see all the different words that are being mentioned, and then you do a proximity. So basically you have metrics that tells you this word is super close to this one. It actually has a shift of 2 characters there, and then you can actually say maybe this is the word because that one that is being written, it doesn't exist. Levenstein distance is an example, very simple, of how you can do this. And actually a lot of misspelling algorithms that you see out there, they are indeed built like this. And they get better and better as you grow a collection of documents, because you know the terms that are more often being said, and you also know that the ones that are very low, you remove them as they're probably typos. All right. So in the beginning, I mentioned stemming and lemmatisation. So what are those about? So my concern is always on, improving the quality of the different tokens that I have, and making sure that I kind of reduce this in a way that I can represent well my documents, but at the same time keeping its information, right? So one strategy to do this is by using stemming. So what is stemming? Basically, it's taking what is known as the base root form, right? So it goes to your words and do things such as this. Having, it says that it will break on have and represent have like this. So I actually here, I resolve a problem with a word, with the verb have, because have is being said on many different ways. And if I didn't use stemming, basically for the algorithm, they are different words. So I would have more columns on my representation. And in this way, I have in one unique, and everything counts in there. So that's the advantage, all right? The advantage is that you reduce the dimensionality a lot. Disadvantage, well, as you can imagine, some words lose their meaning, their semantic meaning. So stemming, it's quite, let's say, radical in the way that it cuts the words. So according to your problem, be aware of this. If I'm doing the example that I gave you for the language recognition algorithm, stemming might be quite a good approach. If I'm doing the reputation algorithm or even sentiment analysis, maybe stemming is not really the best approach, okay? So keeping that in mind. But it does help you to resolve dimensionality problems. What is the difference between stemming and lemmatization? So lemmatization, it has, in terms of processing, it's a lot more heavy. So you will notice the same collection of documents, it takes a lot longer to process with lemmatization than it did with stemming. Also, it does not reduce as much, but it has the advantage of keeping the word meaning. So it will do things such as, for instance, the verb sing. If I have sing in the past tense, such as sung, its lemma will be the verb sing. And stemming will be stem, and having, instead of being have, it will be just H, A, and V, it will be actually have, all right? It will take out problems such as plural and so on, okay? So that's the difference between these two, all right? I advise you to, if you ever use this and you still don't remember, maybe these 2 slides help you, but the best way to see it is see examples, because they are quite different and there's a lot of confusion among them many times. Okay, so so far I just gave you some idea of the different challenges you have when you are processing text. There are many more. And the other message that I want to tell you is you have deep learning in here nowadays. Do they resolve all of this? No, because deep learning needs for you to feed the data and they need to be structured, and deep learning is not doing that. Okay, so I think it's a very good example on the different things we need to do, right? So the advantage of deep learning is that maybe I don't want to bother and I just put it all there, but I always need to do at least tokenization. I will always need to be worried about contractions. So there's a lot of stuff that I still need to worry about before going to the deep learning algorithms, such as, for instance, using LSTMs for different problems, okay? So that's why it's so important for us to know all the different steps. Another thing is terminology. So what I was explaining you so far, you could fit it more like into the feature extraction step, which is, well, I need to get all this raw text into some structured mode. I need to be able to reduce its dimensionality, and so on. But there are other things that we can do. So we can actually transform our data, so more in terms of normalizing it, missing values that we might have, and so on. This is known as feature transformation. And then you also have feature selection, which it means that as soon as I have this format that is more structured, I'm already representing my documents, well, I can actually answer questions such as, which are the features that are more relevant? And this actually helps me again in the problem of dimensionality, but now I'm doing it in a different way. I'm actually looking at my collection in that representation and then taking it out, okay? So if you see these different terms, think about different steps of your work that you are doing. All right, so I want to give an example of what does it mean. So far, I think it was a bit very theory and give you some examples. But when you are working, what does it mean when I'm saying that I'm representing my documents in a space? What is that space? What is this dimensionality that I'm talking about? So you can see it in this way. You have a vector space. If we go for the simple example of the words, it means that here, this vector space, it has all the words that I know. If I have a collection of 100 documents, my vector space will be all the different words that exist within that collection of 100 documents, which can be, for example, 2,000 words. So I will have 2,000 different words here, okay? So if I have this vector space, how am I going to represent my documents? I was telling you about this matrix, right? What is this matrix? So the matrix, you can see it as columns. What are the columns? Well, the columns are all the words that I know in my vector space. So if I have 2,000 words, I have 2,000 columns. And then what are the rows? Well, each row is a document. So that's what you're seeing here below. I get one document, and now I'm going to look at the words that I saw in that document, and I'm going to put some sort of weight. For example, if it happened, 1, if it didn't, 0. So I'll go through those 2,000 words that I have in my vector space, and I'll fill it out with 1 and zeros. Okay? So you have this matrix, and this is how it works. Okay? So if I'm using the bag of words, this vector space has words, and if I'm using, for instance, here the example is the document frequency, it means that on each word, if I see it happening in my document, I'll put it, oh, I saw it once, 1. I saw it happen 2 times, 2 times, okay? So let's go to a more concrete example of what I was just explaining to you. You have here 4 sentences. I'm just relating them as 4 documents. So these are my training documents. I have the sky is blue and sky is beautiful, and so forth. And then I have a test document. So it means that the words in the text document are not used to build my vector space. It's a new document. Okay? So if I look at those 4 sentences, how does it look my vector space? So I will go look at those 4 different sentences, and if I'm using bag of words, so it means that I'm going to put in here all the different words that I saw in there, okay? And in this case, example, we took the stop words, okay? I think we took. The I is not there. Maybe it's my problem, sorry. I forgot the I, love. Okay, so, and beautiful blue cheese is love sky so deep. So these are all the different words that you saw here in the training documents, okay? And how do I represent my documents now? I have this vector space. See the columns are the different words. Usually you sort them out by alphabetically just to make it easier for you, okay? So document 0. Document 0 is the sky is blue and doesn't happen. 0, beautiful 0. Blue 1 is 1 and sky 1 and 2. All right? So if I go, for example, for the document 1, sky is blue and sky is beautiful. If you notice, I have 2 in is, and I have 2 in sky. Why? Because they happen 2 times. And I'm putting here the weight that I represent the different words in my documents is the frequency of each one of them. Okay, so that's why we have a matrix, and that's why if you're not careful enough, these columns grow like crazy, and then you have a lot of zeros. Okay, so computationally it's a challenge, but also it's not even something that you're adding value to it. Okay, all right. So the final example is, I have my text document. It says, loving this blue sky today. So notice that the text document will be projected in this vector space, but the vector space did not know the word loving. So what happens is we are losing this information. So that's why sometimes when you're hearing people saying that I need a collection that is representative of my domain, the reason is this one. Because if it's not a collection that I can learn that is representative, then I have a problem. Because basically what's going to happen is that you are losing that information, because the algorithm will only know this representation. Okay? All right. So I gave an example for document frequency, just a final slide, so to give you an example. There are many different ways of weighting what you see in your documents. You can have the raw count, you can have log normalization, you can have the very popular one, which is term frequency inverse document frequency. So there are different weights that you can put in there. And usually the weights that you use is also related to your challenge, okay? So if I'm using, for instance, this idea of having the collection, for instance, the classification with different domains such as science, history, biology, and so on. So what happens here is that, for instance, TF-ADF might be the way to go, all right? So he's able to distinguish the importance of that term in my documents. I might happen a lot of times, but if my document is huge, then I should actually leverage that. So that's the term frequency. I see the number of times that it happened, but then I divide by all the tokens that I saw in that document. Okay, if I happen 2 times in a document of 200 tokens, it's not as relevant as 2 times in a document of 10 tokens. Okay, so that's what is weighting. But it's also weighting something else, which is really interesting, which is, well, if I have a token that is quite high in terms of weights in my documents, and it doesn't happen in the other classes, so it's happening a lot in history, but then in science it's not. So I want to take that into account. But if I happened a lot in history and in science, well, I'm being mentioned a lot, but I'm actually important to everyone. So it means that I'm not being faithful to my class. So stop words have that behavior. You see words such as and a lot in all the different domains, because it says nothing about the domain and it's actually mentioning a lot. Okay? All right. So word vectors. I think I'm already getting close to the end of the talk, so just bear with me another 5 minutes. Okay? So word vectors, they came up, and why were they so interesting? And actually they were able to provide a lot of novelty to the area, and novelty mainly because they allowed us to do things that before computationally was super challenging. That's one point. And the other point is that they also allowed us to go beyond the capabilities that we had before in terms of algorithms that needed a lot of labeled data, but now we're actually able to put those models on and do things with very low amount of labeled data, but we actually have a lot of good quality models on the output. So those are the 2 main takeaways. So an example from word vectors. So what are you guys seeing here? So think about all those tokens that I was telling you, right? Is what you see here in the gray one. So you have the different tokens. You have in here, it's a dog, cat, lion, and so on. And the word vectors have these dimensions, all right? So the negative part of it is that if I look at these dimensions, I mean, it's hard for me to understand what do they mean. So it's projecting into this space. This is a 4-dimensional space, okay? But what is the advantage here is that it was able to go through the whole collection of documents. And in this space, we are able to see how close dog is to cats and how far away dog is from rats through this 4-dimensional space. all right? But this is how it looks like. And this part that you see here with some colors, which says it's animal, domesticated, pet, and fluffy, sometimes when you are talking about the black box models, some of the work that is done is to bring some explainability to the dimensions that we have. So there's a lot of work on, you know, I produce my word vectors, now I'm going to look at the dimensions and try to give some explainability to it. And that allows me to deliver models when they need some explainability, but when I'm looking at the vector like this, I can't. But if I do some work and I'm able to say that, hey, this dimension is highly related to the concept of animal, and this one to the domesticated and so forth, it's awesome, because then you are able to actually to provide some more insightful information on the output of your model, okay? So that's why you see a lot of work on explainability from word vectors. All right, so this is another example. So I have the sky and the blue, and they are in 10 dimensions, all right? This can actually then, you can think about when you, if you are doing this type of work, you can actually have a lot of challenges. And one of them is the number of dimensions is not exactly the same. So to just try to quickly give you a brief idea on what I mean by this is that when you saw the vector space, it means that all the documents need to be represented exactly in the same way, right? But if I have each word with 4 dimensions, right? And if I have a word such as saying, my dog and my cat are amazing, I have dog and cat. So I have 2 vectors that I know, right? So how do I represent this in one single vector? Because the sentence is, my dog and my cat are amazing, right? So there are different strategies, because right now it's not the weights, it's I have a vector for each word. So one strategy here is to use average word vectors. So basically, you're going to pick up in all the words that I saw in my sentence, I pick up on their vectors, and I see how relevant they were in each dimension, and I have a final weight for that sentence in that dimension. So I would take all the weights that I saw from the first dimension, I would sum that up, and I count it as a weight from everything that was said, for instance, for the dimension of animal. All right, so that's the average word vectors. It's one strategy to have a final vector for your document. Okay. Advantages. Well, this basically allows us to do things like this. I'm going to give you the example. I think it's easier to explain. So I have all these different sentences. They are represented in this space. It's using the word vectors. So I'm able to do things like this. Sentence 0 is, I bought bananas at the grocery shop. Sentence 1 is, we purchases apples from the corner store. And the word vector says that they are super close, 0.84. But if I had used the traditional algorithms, it wouldn't have happened this way. Why? Because I have store, and the other one, it has grocery. And the first one says bought, and the second one purchased. So traditional approaches would not be able to know that semantically these words overlap. All right, so this is a very good example for you to understand why we are so eager to use word vectors. All right, and not so long ago this showed up, and this was back in 2013. So since then the area in NLP grew like crazy in terms of what we do in deep learning, and you've seen more and more attention and more pre-trained models that you can use for your work, which is, if you think about a pre-trained model, most of us do not have the computational power to do it. But this pre-trained models is made available to you. You can use it, and then you can tune it on top of that if it's not good enough for your challenge, okay? And this allows us to do something that is scaling, right? So in the past, we had this green line, and now with neural networks, we are able to scale up. So that's actually one of the biggest advantages of using deep learning in NLP. Again, it depends on your problem, because if your problem does not need to scale up, then you don't need this complexity, okay? All right, so I'm almost ending. So I just wanted to also show you the advantage of deep learning for translation. So this was again another of the breakthroughs. So we had a lot of translation models in the past. What is the difference now? Well, with deep learning, we are able to do this in an unsupervised manner. And basically, you could put it in this way: collection of documents here in one language, which is this X space, and then you have the other one. This W is what you are learning, and it actually allows us to overlap, and we actually know the translation of one another. All right, I'm not here explaining the algorithm itself, but what I'm telling you, they are really amazing. All right, this that you're seeing in this plot, blue, it's a metric that is used on the area of words translation. Okay, what you see in the x-axis is the parallel documents. Parallel documents is a document that is a translation of each other in different languages. So these are highly expensive. What was the problem in the past? I could not scale up because it's very expensive to get more and more documents. So what you see here is you have in these lines, horizontal lines, are the unsupervised models, okay? So what you can see is that we can actually have a lot of a very good performance. So if you see this performance here, right, you could say, okay, it's only 15. Yes, but look at the size of the data that I need to get here. So I can only go beyond that if I have this amount of parallel training documents, 10 to 5, it's a lot. So if you don't have that, well, use deep learning. That's why a lot of people are using. Okay, if you have that, of course, then you should use the other approaches because they are able to learn better, right? But then you could also say that, well, you can use a combined approach. So what people are doing now is using hybrid approaches, right? Because then you can take advantage of, let's say, the both worlds. Okay, this is, I'm going to skip a bit this. This is great news. This works very well with languages that are very close to each other. It's not the same if you have languages that have different backgrounds. So for instance, if you have Greek or Russian or Turkish, it's more challenging. So it's not like this is the resolves all the problems that we have, but it's quite a big breakthrough. And this is just some benchmark results that you have. These are the performance with human. BERT is deep learning large, so it means it's already a pre-trained model that it's huge. But look how close it is. It's amazing. All right. Okay, I'm just gonna close. Thank you so much for your time and for bearing with me these extra minutes.